Okay, so last time we were here, we're about to get into a discussion of another trend that we can observe with respect to the periodic table going across a period and down a group. Now, the particular physical property that we'll be looking at here is known as the ionization energy, all right? And as you can see on the screen, the definition is given for the ionization energy. It is the energy that is required to remove an electron from a ground state gaseous atom, all right? So imagine you have an atom which is in a gaseous state and it loses an electron. In order for that to take place, energy is required, all right? And as you can see in this hypothetical example, when the electron is lost, of course, a plus charge is left behind on the ion that is formed. And then you can have the removal of other electrons. So if you have more than one electrons, you can successively remove each electron. And basically, with each removal of an electron, a certain amount of energy is required. So the term that we use to go back to this here. The term that we use for the ionization energies here, respectively, for the removal of each electron. To remove the first one, we call that energy required the first ionization energy. To remove the second one, the energy required is the second ionization energy, and so on and so forth, right? So that's basically what ionization energy is all about. Now, turns out that for all atoms, regardless of what the atom is, the order of magnitude of ionization energy increases as you remove one and then the other and so on. So as you can see here, I2 is less than I1. I'm sorry, I1 is less than I2, and correspondingly, I2 would be less than I3. So therefore, basically what we're saying here is that more energy is required with the removal of each electron, right? So that indicates that there's an increase in difficulty of removing an electron each time as you move from one electron to the other, all right? Another thing that you'll notice is that there's a large increase in ionization energy after you remove the valence electron. So in other words, to remove one valence electron, right, a certain amount of energy is required. To remove another valence electron, even more energy is required. But if, let's say, those two electrons are in the valence shell, and then you start going into the inner shell, then there'll be an increase in the amount of energy required to remove the third electron, all right? And the reason why, of course, is because after you remove the valence electrons, which are in the outermost shell, then basically the electrons that are closer to the nucleus in the inner shells would be more tightly held by the nucleus, and therefore more energy, a significant amount of energy, much more than that was removed before, would be required to remove those electrons, all right? So let's talk about certain trends that you'll observe when it comes to ionization energy. The first one we're going to observe is that the ionization energy decreases as you go from top to the bottom of any group in the periodic table, right? Now, why is that occurring? Well, if you think about it, as you go down any group, the distance, or I should say the average distance of the valence electrons from the nucleus would increase, all right? Not only that, but you also have the inner core electrons shielding the valence electrons from the nucleus, right? So as you go down the group, the number of inner core electrons increases, shielding the valence electrons, and therefore it is easier to remove the valence electrons as you go down a group, all right? So that's basically what happens as you go down a group. The ionization energy decreases. Now, and here they're referring to specifically the first ionization energy, all right? Now, what happens when you go across a period left to right? Generally speaking, what you'll find is that the ionization energy, the first ionization energy will increase as you go from left to right, but there are certain exceptions, and we're going to point out those exceptions shortly. But generally speaking, what you'll see is that there's a general increase in the ionization energy as you go from left to right. And the reason for that is, as you go from left to right of any period, and we saw this before last time, you're increasing the nuclear charge, which would result in a greater attraction for the surrounding electrons, and therefore it becomes progressively more difficult to remove the valence electrons, because as you go from left to right, those electrons will be drawn closer to the nucleus, right? So That's basically the general trend that you'll observe as you go from left to right of any period. The ionization energy, the first ionization energy generally increases as you go from left to right of any period, all right? So let us look at some examples right here. So I mentioned before, right, that after the valence electrons are lost, so a certain amount of energy will be required for that, then there's a significant jump in the amount of energy that is required to remove any of the inner core electrons, right? So just to highlight an example of that, now let me just explain what we have here. What we have here is a table which gives you the first and second ionization energy of elements in groups 1A and 2A, all right? So these are the values of first and second ionization energy for lithium and beryllium, same values for sodium and magnesium, similar values for potassium and calcium, and so on and so forth, right? Now, if you were to compare, let's say, the ionization energy first and second for potassium, right? The value for potassium for the first ionization energy is 419 kilojoules per mole. And then to remove the next electron, there's a huge jump from 419 to 3051. All right? Now, if you compare that to calcium, in the case of calcium, to remove the first electron is 590, and then to remove the second electron is 1145. So you'll notice that the difference in the first and second ionization energy in the case of potassium is larger, significantly larger compared to the difference in the first and second ionization energy of calcium. Why is that so? Well, in the case of calcium, if you remember, and if you look at the periodic table, calcium is in group 2A, right? So therefore, calcium has 2 electrons on its valence shell. So therefore, a certain amount of energy is required to remove the first electron, and then a great amount of energy is required to remove the second electron, but both electrons are removed from the same shell, right? So the difference in energy for the first and second ionization is not that large. However, in the case of potassium, potassium is in group 1A, which means that potassium has 1 valence electron in its outer shell. So therefore, a certain amount of energy will be required to remove that electron. And then now, in order to remove the next electron, which will be in an inner core shell, a significantly higher amount of energy would be needed. So that's the reason why there's a significant difference between I1 and I2 in the case of potassium compared to I1 and I2 in the case of calcium, right? In the case of calcium, both electrons are being lost from the same shell, but in the case of potassium, the first electron is lost from the valence shell, and then the second electron, which is on average closer to the nucleus, will be lost from the second shell, and therefore the amount of energy required in that case would be significantly higher, all right? Okay, so that's basically the trend that we observe with respect to first and second ionization energy. Now, as I mentioned before, as you go from left to right of any period, the ionization energy generally increases, right? But as I said before, there are some exceptions to this. So we're going to look at these exceptions and see how we can explain that. Okay, so, excuse me. Our focus here will be on the first ionization energy. Starting off with lithium, right? Which has the first ionization energy is equal to 520. And then as you go from lithium to beryllium, the first ionization energy increases. No surprise there, because as we said before, going from left to right of any period, on average, the ionization energy would increase. But we notice something here as we go from beryllium to boron. As you go from beryllium to boron, what happens? The ionization energy decreases kind of slightly, right? Now, why is that so? Well, if you think about the electron configuration of beryllium compared to boron, in the case of beryllium, beryllium has an electronic configuration of 1s2, 2s2, right? Whereas in the case of boron, the electron configuration of boron is 1s2, 2s2, 2p1, all right? So in order for you to get 1 electron being removed from the beryllium, you'd have to remove an electron from the 2s orbital here, right? So one of these 2 electrons will be removed in order for you to expend your first ionization energy. In the case of boron, this electron would be the electron that would be lost when you're ionizing it, right? So if you compare the relative distance between the electrons here from the nucleus compared to the electron here, what you'll find is that this electron here would be on average further away from the nucleus, right? And because it's further away from the nucleus, that means that it's easier to remove, and therefore the ionization energy would be less, all right? So as I think I have it stated here, the ionization energy drops as you go from 2A to 3A, so beryllium to boron, for example, right? And the reason for that is that the electron being lost in the case of the boron is in a 2p subshell, which is on average further away from the nucleus compared to the electrons in the 2s subshell, all right? So that's the reason why you see a slight drop in ionization energy going from beryllium to boron. And in the case of magnesium and aluminum, again, there's a slight drop for pretty much the same reason, all right? Now, continuing the trend, going from boron to carbon, the ionization energy increases. Going from carbon to nitrogen, again, the ionization energy increases. So no surprise there because of what we said before. But again, we see another slight drop going from nitrogen to oxygen. So nitrogen is 1402 in terms of its I1 value, and the corresponding value for oxygen is 1314. So how do we explain that? All right, so again, we have to go to the electron configurations of those two elements. Now, nitrogen has an atomic number of 7, which means that for nitrogen, the electron configuration would be 1s2, 2s2, and 2p5. Now, what I'm going to do is, instead of writing down the electron configuration in the SPDF notation, I'm going to use electron in boxes, all right? So it would be 2p3, not 2p5. So these are your 2p subshells, 1, 2, 3. So that's how the electrons will be distributed in the case of nitrogen. Now, in the case of oxygen, the electron configuration would be 1, 2, 3, and then 4, all right? So the question is, which electrons will be lost upon ionization? So these are the 2p subshells for the oxygen, right? So in the case of nitrogen, any one of these electrons can be lost, right? And therefore, energy would be required to do that. And according to the data here, that energy is 1402 kilojoules per mole, right? In the case of oxygen, however, what you'll find is that the electron that is more likely to be lost upon ionization will be one of these two electrons here that are sharing the same p orbital. Now, electrons are like charges, and therefore what will happen is that there'll be some repulsive force between them. And because of that repulsive force that is between these two electrons that are sharing the same orbital, that means that it is easier for the oxygen atom to lose one of those two electrons compared to the nitrogen losing any one of these 3 electrons. All right? So electrons will be lost from the 2p subshell in both cases. But in the case of oxygen, because of the repulsive force that is existing between those 2 electrons, then it is easier for the oxygen to lose that electron compared to the nitrogen losing that electron. And for that reason, the ionization energy of oxygen will be slightly less compared to the ionization energy for nitrogen. And again, I'm referring to the first ionization energy, all right? So those are the exceptions. Let me see what I have here. Those are the exceptions that kind of buck the trend in terms of the increasing ionization energy as you go from left to right of any period. So this is, oh, you can't see that. Let me just clear this so that you can see what the writing here says. The electron being removed now is a p electron, which has a higher energy, and it is easier to remove than the s electron, right? So therefore, that explains a slight drop as you go from nitrogen to oxygen, right? Okay, any questions about this? Any questions? Any questions? Any questions out there in Zoom? Okay, so that's one trend that you need to be aware of. And I think, excuse me, I think the next slide. Oh, this is just a graphical display of the trend that I just mentioned. So what I was describing, well, let me first explain what this is. On the y-axis, you have the first ionization energy plotted. On the x-axis, you have the atomic number, right? So we were looking at period 2, which starts with lithium, right? So as we said before, lithium, then beryllium, right? The ionization energy increases, and then there's a slight drop to boron, and then you have boron, carbon, nitrogen, and then from nitrogen to oxygen, there's a slight drop, and then from nitrogen, you have carbon, and then what's the next element? I think the next element is hydrogen, helium, beryllium, boron, carbon, nitrogen, oxygen, and then fluorine, and then neon, right? So that's basically, this part here basically is what we were just talking about. And there's a similar trend in the case of period 3, which starts with sodium and end with argon. And again, there's a slight drop from sodium to magnesium, there's an increase, but there's a slight drop from magnesium to aluminum for pretty much the same reason as we described here. The only difference is that we're dealing with a higher shell. So we're talking about going from 3s to 3p here, and then there's another slight drop here, going from, if I'm not mistaken, from phosphorus to sulfur, and then it continues to argon at the end of that period. For the rest of the periodic table, it's a bit more jumbled, so we won't go into that region in terms of the trends. But again, let me just say that the general trend is that as you go across any period left to right, the ionization energy increases, with the exceptions that I mentioned before. Okay, so let's look at this example. This question says, without reference to the chart, basically just using the periodic table, and I made sure to bring my own copy since we don't have one here in this classroom. It says, arrange each set of elements in expected order of first ionization energy. Increasing, I should say, first ionization energy, right? So basically, you're going to start in each case with the lowest to the highest, all right? Lowest to the highest, based on the positions of the elements in the periodic table. So in the case of A gives you magnesium, silicon, and sulfur, right? So remember now, well, let me just see where they're. Oh, okay. So based on the periodic table that I have here in front of me, these elements are in the same period, right? So remember I said that the ionization energy generally increases as you go from left to right of any period, right? So which one would you expect, if you have your periodic table in front of you, which one would you expect to have the lowest ionization energy? Which of these three you'd expect to have the lowest ionization energy? And they're in the same period.
The lowest?
The lowest, exactly. It's
Magnesium.
magnesium first. Okay, what's the next in line?
Silicon.
Silicon, and then sulfur will be the end. Right, okay. That's very good. Okay, B, they gave you arsenic, nitrogen, and phosphorus, all right? So based on their positions in the periodic table, they're all in the same group. I remember we said that the ionization energy decreases as you go from top to bottom of any group, all right? So which of these you'd expect to have the lowest ionization energy?
AS,
Arsenic, followed by?
nitrogen, or no,
Mm,
phosphorus.
phosphorus, then nitrogen, all right? Okay, very good. And then the last one, C, they gave you arsenic, germanium, and phosphorus. Okay, so based on what I see here in front of me, hold on, arsenic, germanium. Okay, So germanium is to the left of arsenic and phosphorus is above arsenic, right? Let's see here. Which of these would you expect to have the lowest first ionization energy?
It decreases from top to bottom and decreases from right to left, so germanium would be the low.
Okay, so germanium would be the lowest, followed by what?
Arsenic.
Followed by arsenic, and then, of course, phosphorus, all right? And that is how that is done. All right, very good. Okay. Let me clear this and scroll down. Okay, so another property we're going to look at, and we won't even spend much time in it with this. In fact, I won't even go about explaining this to any great detail. Electron affinity. Let's define what we mean by this term is. So by definition, electron affinity is the energy change that occurs when an electron is added to a gaseous atom. So this can be seen as the opposite of ionization energy, because if you remember, the definition of ionization energy is the energy required to remove an electron, right? In the case of electron affinity, it's energy required to add an electron to a gaseous atom, right? So in other words, if your atom is M, you add an electron and you get a negatively charged ion or an anion. And the energy change for that is what we call the electron affinity, all right? Now, electron affinity values are necessarily negative because pretty much when you add electrons to an atom, that ends up with the energy change being an exothermic, right? So therefore, delta H, or I should say the electron affinity, would be negative for that change, right? And what you'll find is that nonmetals tend to have a more negative value for electron affinity compared to metals, right? And that's because nonmetals, they like to form anions, all right? So what you'll find, generally speaking, is that the electron affinity will be more negative as you go from left to right of the periodic table and from bottom to top of the periodic table, all right? So that's basically all I'm going to say about that. And I think I have some numbers here. Electron affinity values are very difficult to determine. So there's not many values that one can show, but basically this is the trend that you'll observe. Again, there are some exceptions, which I won't even go into. But basically, the general trend is as you go from left to right, and as you go from bottom to top, the electron affinity becomes more negative. All right, and that's all I'm going to say about that, all right? When it comes to metals, as we probably met before, they usually have a small number of electrons in their valence shells, no more than 3 in their valence shells for the representative elements. And an example of this would be aluminum, of course, which has 3 valence electrons. So when it loses those 3 electrons, it forms the aluminum 3+ ion. And basically all S block elements and all B and F block elements, and there are some P block elements that are metals. So most of the elements in the periodic table are metals, right? So the next thing we're going to talk about, the next trend we're going to talk about is what we call the metallic character, which is related to both the atomic radius and the ionization energy. And basically the metallic character trends in the periodic table are as shown in this diagram right here. As you go from top to bottom of any group, or as you go from right to left of any period, the metallic character increases, all right? So that's basically the trend as far as the metallic character of elements in the periodic table are concerned as it relates to where they're located in the periodic table, all right? And then when it comes to nonmetals, they tend to gain electrons to form negative ions. And all nonmetals, excepting hydrogen and helium, are P block elements. And in terms of the non-metallic characters of elements, it's basically the opposite of metallic characters, right? In other words, going from left to right and going from bottom to top of any group, the non-metallic character increases, all right? So that's basically the trend as far as non-metallic character is concerned. And then we have a minority group of elements known as metalloids. Metalloids are elements that have some characteristics in common with metals and other characteristics in common with nonmetals, right? And those elements are located on one or the other side of this stepwise line here. So most periodic tables have this stepwise line. which basically represents the line of demarcation in the table between the metals on the left, non-metals on the right. But there are some elements that straddle either side, which are called metalloids, right? And these are the 7 metalloids that are in the periodic table, all right? And as I said before, they have some properties in common with metals and some in common with non-metals. So this is basically a summary of all the trends that we have discussed, all right? So just to briefly recap, as you go from left to right of any period, this is what you observe. The metallic character, the non-metallic character increases. The electron affinity becomes more negative, and there's also a corresponding increase in ionization energy, all right? If you go from right to left, there's an increasing atomic radius, and the element becomes more metallic, all right? Going down any group, again, the atomic radius increases, and the element becomes more metallic, all right? And then going up any group, what you'll find is that the non-metallic character would increase, the electron affinity will become more negative, and also there'll be an increase in the first ionization energy as you go from bottom to top of any group, all right? Now, let's look at some examples here. Now, this question says, in each set, indicate which is the more metallic element. So remember now, the metallic properties increases as you go from right to left of any period and down any group, all right? So the first one, A, is barium. They gave you barium and calcium. So which of these two would you expect to be more metallic?
Said barium and calcium.
Yeah. Which would be more metallic? Remember, the metallic character increases as you go down any group. And barium and calcium are in the same group, so
Yeah, I was totally looking for barium. You said it decreases as you go down?
increases.
Increase. So
I'm sorry, decreases. My bad. No,
Increases. as you go
increases. I'm
down.
thinking of ionization energy. I'm sorry. Right, so it increases as you go down any group. So the answer would be what?
So calcium would be less metallic and barium would be.
Right, so barium will be more metallic. That's what they're asking for, more metallic. Okay, what about antimony and tin, SB and SN? Now, in this case, you're looking at trends going across a period, and it becomes less metallic as you go from left to right of any period.
SN is more metallic.
Oh, okay, very good. All right. And then we have germanium and silicon. Where's germanium? Okay, germanium is there. Not silicon, I'm sorry, sulfur. So which would you expect to be more metallic?
Germanium.
Germanium, exactly. And that's it. All right, very good. Okay, let me clear this. Let's go down. Okay, just some general information here about the elements in group 8. They're called noble gases, or noble elements, or inert elements. And they're so called because they're very unreactive. And the reason why they're unreactive is because they have a full octet of electrons on their outer shell in their atoms, with the exception of course, helium, which has a duet, 2 electrons on the only shell in the case of helium, which is also full. So therefore, these elements are very unlikely to enter into any reactions. In fact, what you'll find is that there's some inert elements that can form compounds, but you have to employ some real special conditions in order to make these compounds and maintain them, because once these compounds are exposed to the atmospheres, then they basically decompose. So pretty much all the elements in group 8, people have made compounds with them, with the exception, as far as I know, I haven't checked this recently, but as far as I know, nobody has successfully made any compounds with helium or neon. So these are like the most inert elements in the periodic table. But people have made compounds like with xenon, they have made compounds like XeCl4, XeO42-. These compounds have been made, right? Argon, what was it? Argon, if I remember correctly, argon Cl something, I don't remember, but those compounds have been made, right? But you'd have to employ some special conditions and instrumentations and so on in order to make them and keep them, all right? Okay, so so that's it for group 8 elements. Not much to say about them because, you know, they're not very fun to watch because they don't do anything really. Now, we learned about the electron configuration and of atoms. And what you'll find is that in the case of metals, because they have relatively low ionization energies, it is very easy, relatively speaking, to promote electrons from lower shells to higher shells. And then what will happen is that when those electrons fall back to their original shells, they emit radiation of a particular color. And that is true for the metals that you see here. Now, basically what we do in order to observe these colors is that we take a piece of what we call nichrome wire. Nichrome wire is basically an alloy of nickel and chromium. And basically what we do is that we dip one end of that wire into a solution containing these ions, and then we stick that wire with the solution on it in a Bunsen flame, and you're going to see the flame producing different colors. And you can identify the particular ions in the solution by the colors as you can see here, right? So calcium give like an orange-red color, barium give a observable characteristic green color, and so on and so forth, all right? Now, as stated here, when it comes to nonmetals, they have higher ionization energy values and therefore require higher temperatures in order for us to see, well, we won't see it actually, in order for these colors or different radiation of different types emitted, right? And in the case of those elements, very often we cannot see it, but basically we can detect it using instruments. And what you'll find is that the radiation that's emitted would be in a region outside the visible region, such as the UV region of the spectrum. Okay, and then we're going to look at another property with respect to group 7A elements, and that is their oxidizing properties, right? So if you remember, oxidizing or oxidation involves loss of electrons, reduction involves gain of electrons, all right? So what you'll find is that halogens have a high affinity for electrons, so therefore they tend to oxidize other substances that comes into contact with it, right? So what you'll find is that the oxidizing power increases as you go up the group of 7 or group 7A, right? So group 7A has bromine at the bottom here, has iodine below that, and then you have chlorine and then fluorine, right? So the oxidizing power increases going up the group. So this is oxidizing power, all right? So what that means is that fluorine is a stronger oxidizing agent compared to all the others, and so on and so forth, right? And therefore, what you'll find is that because fluorine, for example, is a stronger oxidizing agent, it will basically remove electrons from the other elements that may be present in a particular compound, and by so doing, displace those elements below it from their compound. So for example, and that is being demonstrated here, right? In this these two pictures here. Hold on 1 minute. Basically, what this person is doing is bubbling some chlorine gas into a solution containing iodide ions, right? So because chlorine is a stronger oxidizing agent compared to bromine, chlorine will displace bromine. So therefore, if you have chlorine and you bubble it in a solution containing bromide ions, then what will happen is that the chlorine will gain the electrons from the bromide to form chloride, and you're going to end up with bromine being formed, right? And what this person did was that they had the solution of bromine, of iodide, in, I think, carbon tetrachloride or something like that. And then when they bubble the chlorine in it, the bromine that is formed will basically end up in the carbon tetrachloride solution, and therefore that's where you end up with this. Oh shoot, it wasn't bromide. I'm sorry, it's iodide. Let me correct that. This is iodide, not bromide. So this is 2I minus, and this is I2. So it's an iodine that basically, when dissolved in the carbon tetrachloride here, you end up with this purple color, all right? So that's just basically the trend in terms of the oxidizing power of the halogens. The oxidizing power increases as you go from iodine to fluorine in that group. Okay, let me clear this again.
So the oxidizing power increases as you go down,
No, goes up.
as you go up. Okay.
Yeah. Okay. Let me clear this. And then when it comes to the metals, what you'll find, of course, is that they tend to display reductive or reducive power. Basically, what you'll find is that because metals have lower first ionization energy, they tend to give up electrons relatively easy, right? And what you'll find is that as you go down, especially the S block elements, groups 1A and 2A, as you go down those two groups, the reducing power of those elements increases, right? So that can be demonstrated if you look at the reaction. No, I'm not sure what metal this is. I think it is potassium, but I could be wrong. Let me see here. Yes, it is potassium. Potassium, very reactive, right? Because it loses the valence electron very easily. It reacts with even the air when it's exposed to it. So when we're storing potassium and sodium, we usually store it in oil, right? It doesn't react with oil, and therefore it remains stable under those circumstances. But once you remove it from oil, at first, like potassium, for example, at first it looks shiny, and then eventually it's going to look less shiny. And that's because the potassium reacts with the oxygen from the atmosphere to form potassium oxide. This is a violent reaction. If you add potassium to water, if you take a very small piece of potassium and add it to water, it starts fizzing. A very violent reaction eventually will occur where the potassium will react with water according to this equation. Potassium plus H2O will give KOH plus H2, right? So hydrogen gas is formed, and to balance this, we need a 2 here, a 2 here, and a 2 here, all right? So that's what happens. And of course, hydrogen gas is formed as a result as well, right? And what you'll find is that this sort of reaction is increases going down the group. So in the case of group 1, you have lithium, and then you have sodium, and then you have potassium, and then you have cesium, right? This reaction here that I just described increases as you go down that group. And that reflects the fact that as you go down the group, the atom will lose electrons quite easily because the electron in the outer shell is further and further away from the nucleus, all right? And there's a similar trend for group 2 as well, all right? Okay, and that's as much as we're going to talk about as far as that is concerned. Okay, so let's talk about, I think this is the last topic in this chapter. Let's talk about the difference between acidic, basic, and amphoteric oxides. What definition do I have first? Acidic oxides, these are oxides that produce an acid when it is added to water, all right? And these are typically non-metallic oxides, all right? Basic oxides produces bases when added to water, all right? And these are typically metallic oxides, all right? And then an amphoteric oxide can react with either an acid or a base, all right? And what you'll find is that certain metals or elements would form amphoteric oxides, such as beryllium, aluminum, and so on, the ones that are, what do you call this, yellow colored, these boxes right here, right? But again, as far as acidic oxides are concerned, they typically are oxides of nonmetals, while the basic oxides are oxides of metals. All right, and that's pretty much it for this chapter. So, oh, somebody's saying something. Oh, I'm sorry, Mr. Hernandez. I have this bad habit of not paying attention to the messages. But you're right about what you said in answer to the question that I asked. Okay, so let me get out of this and get to the assignment. Oh, before I get to the assignment, it just so happened this past weekend that I was scrolling through Facebook, and there's a Facebook page, chemistry. Well, there are several chemistry Facebook pages that I'm a. Oh, shoot. I thought I saved it. Hold on, let me see here.
Acidic oxides are made from nonmetals.
Yeah. There is, oh, shoot. Oh, here it is. I know I saved it. Okay, let's look at this here. So it just so happens, and I said I must show you guys this, right? So this is a summary of the trends that we just talked about, right? But one of them is wrong. One of them is incorrect. Can you tell me which of these is the incorrect one in terms of the trends? Exactly. This one right here. What did we say about the metallic character?
It decreases as it goes
it's-
upward.
Exactly. It decreases as it goes upward and also decreases. Exactly, right. So it should be there. You should be pointing the other way, right? Exactly. So this underscores the importance of being, paying attention to those online sources. Believe me, this is not the first error that I've found or discovered when it comes to, online sources. So I thought of giving you guys this as a question, but I decided against it and just show you guys this. All right. Okay. Let me go to the assignment. And as I recall, we got as far as okay, so I think we completed oh, another thing too. I think I told you guys I was gonna check on which one of these. There was one that I got stuck on for part C. I think it was C. I think it was this one right here, if I remember correctly. In any case, I don't remember the answer I told you, but the answer is, let me write it down here. Okay, so the answer for this one is Al less than K plus less than Cl minus less than S2 minus. That's the answer. All right. I think I had an issue with, if I remember correctly, where the aluminum is placed. So the aluminum would be of the smallest size or radius. All right. Okay. So with that said, let's move on to the next page. And the question says, define ionization energy. And the answer is what?
It's the energy required to remove an electron from a ground state gaseous atom.
Exactly.
That's a mouthful.
It's the energy required to remove an electron from a ground state gaseous atom. All right. Okay, so the next question is asking, what trend in the ionization energy do you see as you go down a group/family on the periodic table? And the answer is decreases. And the question that is asked next is, what causes this trend? So what happens as you go down from one element to the next down a group?
It's because the N increases, and so the valence electron is farther from the nucleus.
Right, N increases. And the valence electrons, or I should say the distance between the nucleus and valence electron increases and therefore the attractive force decreases as well. Making it easier to remove that electron. I think that is sufficient in terms of completely answering this question. All right? Okay, so that's basically the reason why, as you go down any group, the ionization energy decreases, because as you go down the group, the distance between the nucleus and the valence electron increases, the attractive force between those two decreases, and therefore it's easier to remove the valence electrons as a result. All right? Okay, let me clear this and move on to question number 4, which says, what trend in ionization energy do you see as you go across a period? And the answer is what?
It increases from left to right.
Exactly. So it increases as you go from left to right. All right? And the question now is, what causes that trend? So what is happening as you go for the atoms? What is happening as you go from left to right, one element to the next, across that period?
The letter orbital with the valence electrons gets higher.
I'm sorry, repeat that?
The orbital for the valence electrons the orbital gets higher, so they're easier to remove, because you have, like, as you move from left to right, everyone's in P.
No, it's not easy to remove. It becomes
Yeah, it increases, so they're hard.
right. So
hard.
what makes it hard to remove the valence electron as you go from left to right of any period? There are two things you're doing when you're going from left to right. You're adding an electron to the same shell, but you're also adding a proton to the nucleus, right? So how does that make the trend increasing as you go from left to right as far as the ionization energy is concerned? Let me start you off. So going from left to right, an electron is added to the valence shell, and a proton is added to the nucleus. Okay, so what next? What should I say next after that? I'm adding a proton to the nucleus, and I'm also adding an electron to the valence shell, and therefore what? If I'm adding a nucleus, I'm sorry, if I'm adding a proton to the nucleus, and I'm adding an electron to the valence shell, then what would be the consequence of that?
The attractive force.
Exactly. And so therefore, the attractive force would increase between the two, will increase between the two, and the valence electron would be harder to remove. The valence electron will be harder to remove. And that's it. That's why the ionization energy, and remember again, that's generally speaking, remember the exceptions we mentioned, but generally speaking, that's the trend, all right? So basically going from left to right, the changes that will occur in the atom is that you're adding one electron to the valence shell, you're adding a proton each time to the nucleus. Therefore, there'll be an increased attraction between the nucleus and the surrounding electrons, including the valence electrons, and therefore it becomes progressively more difficult to remove the valence electron, and therefore that's why the ionization energy increases going from left to right of any period. All right? Okay, so that answers that. So if you understand that, then you should be able to answer all of number 6, right? Number 6 says circle the atom in each pair that has the greater first ionization energy. Circle the atom in each pair that has the greater first ionization energy. And the first one is lithium and beryllium. So if you look at lithium and beryllium, they're right next to each other. Lithium first and then beryllium to its right. So which of these two would you expect to have the higher first ionization energy?
Beryllium.
Beryllium, exactly. Okay, very good. What about sodium and potassium? Which of these two would you expect to have the highest, or I should say higher, or greater first ionization energy?
Sodium.
No. Going down the group. Oh, yeah, you're right. My bad. I'm sorry. You're right. Sodium would be the one with the first ionization energy, which is higher. What about chlorine and silicon? Which of these two you'd expect to have the first ionization energy to be greater?
Chlorine.
Chlorine, absolutely right. Okay, calcium and calcium and barium. Which you'd expect to have the first ionization energy, which is higher?
Calcium.
Calcium. Okay, very good. And then we get to phosphorus and argon. Okay, where's phosphorus?
They're both in group 3 on the.
They're both in period 3. Okay, somebody's
Yeah, period.
saying something here. Oh, again, I'm late to answering you, observing your answers, but you're correct. Hold on. Actually, Miss Anwar is not correct. In terms of, I think both Anwar and Hernandez were trying to answer D. The answer is calcium, not barium. Because calcium is above barium, so therefore calcium would have the first ionization energy that's higher. All right? Okay, I'm going to try to do better in terms of responding to your text. Okay, so we were looking at phosphorus and argon. So they're both in the same period, but which one would have the higher first ionization energy?
Argon.
Argon, yep. And then lithium and potassium. Lithium, okay, so that's it as far as those are concerned. Okay, so let me clear this. And then in number 7, it says, for each of the following set of atoms, rank them from lowest to highest in terms of the first ionization energy. All right, so you're going to start from lowest to the highest in each of these. First ionization energy. All right, so let's look at the first one. In the case of A, you have magnesium, silicon, and sulfur, which just so happens to be the same period. So which would have the lowest first?
Magnesium.
Magnesium, followed by silicon, followed by sulfur. So basically the same order as given. What about B, magnesium, calcium, and barium? Which would be the lowest?
The lowest would be barium.
Barium, followed by, and then of course, okay, somebody's responding here. Okay, so who is this now? Yes, Miss Anwar. Yes, you're correct. So it's barium, calcium, and then magnesium. Okay, very good. And then the next one, which would be the lowest first?
That's bromine.
Bromine, followed by
Chlorine.
chlorine, followed by fluorine. Okay, very good. And then what about D? No, let me see. Barium is, where's barium? Barium is there. And then copper is further up.
It's under group 1B.
Yeah, and then neon is all the way to the right, further up. Okay, so which would have the lowest first ionization energy?
Barium.
Barium, followed by
Yeah.
neon. So the same order as given, neon and E. Okay, and then the last one is silicon. Where's silicon? Silicon, phosphorus, and helium. So which you'd expect to have the lowest first ionization energy?
Okay.
Silicon, followed by phosphorus, followed by helium. Okay. And that's basically how that is done. All right. So basically, we're finished with chapter 8. And according to the syllabus, you should have gotten your first test this week. But again, I'm going to put it off until next Friday. All right. And let me just check something here, because I know I've sent you back some stuff. I don't remember what I sent back. Let me see here. So the last test was based on chapters. Let me see here. Last test was based on chapters 3, 4, and 5. All right. And so so 6, 7, and 8, which is what we just completed, will be what the next test will be based on. Before I forget, let me just set up a Dropbox for this one. So for assignment 8, okay, so okay, so I'm going to set it due on Friday. Let me scroll down here. So okay. So by Friday, this one needs to be submitted so I can grade it and get it back to you ASAP so that you can have that to review. All right. So I'm going to post an announcement later on this evening, giving the date for your next exam, which will be on the 21st. Let me just check and make sure. Yeah, the 21st, which is next week, Friday. All right. All right. I think I'm going to stop here for today. When we get back, we're going to start with chapter 9. All right. Which deals with molecular structures and all that good stuff. So that's it for today, unless you have any questions you want to ask, or somebody says something here online.
Yeah, that was gonna be my question too, is when are we doing the next test?
I'm sorry?
When are we holding, when is the next test?
21st.
21st.
Yeah, that's so next Friday, yeah. And that would be based on
That's the last class we'll have before Thanksgiving, right?
I think so, yeah. And then we're going to see what we can accomplish as far as the rest of the chapters are concerned. And then the next test will be the final exam. Yes, Miss Anwar, I think it's 6, 7, and 8. Okay. Oh, I won't even leave here. I have a meeting online. Might as well stay here and attend it. All right, so that's it, folks. For you guys out there in Zoom, I'm going to sign off now.